All right, let's get started. Let's do this. Okay, so we want to talk about trees today. Whew, we're getting through this. One more week, we can all make it to spring break. I have been ready for a break. So we just had, I meant to talk about this on Friday, but we just had another barrage of deadlines on Friday. We have another couple deadlines coming up today. Actually, no, I did talk about this on Friday, didn't I? I think Task 3 final deadline, that's the first big checkpoint of the course. I did talk about that. So hopefully we're all hitting the Task 3. I guess it was the Task 3 expected deadline would be the first big checkpoint. I don't know if it's... I do need more tests. So the problem is my code works great for starting and stopping the music until the Wi-Fi is really, really crappy, which is usually the environment that I'm in production. So whenever I test it at home, I'm like, why didn't it work at lecture day? I test it at home with blazingly fast Wi-Fi, and it's always fine. But now I don't know if it's the Wi-Fi going slow or Spotify. I heard Spotify was itself was having issues, which is complicated. But anyway, so we have these deadlines. The next big one, this is the next big checkpoint to figure out who's going to stay with the course past Task 3. So hopefully we're all making it past there. We had the Task 1 and Task 2. We unfortunately lost, I think, 4 students in this section. 4 students in this section from the Task 1 and Task 2 final deadlines, which is pretty damn good, I think. Out of 130 is good, but it's also only Task 1 and 2. Task 1 and 2 are pretty easy. To not make it past those 2 is, I don't know, pretty bad. But Task 3 is the first challenge. I'm sure you're all realizing that by now. Task 3, a bit more tougher. Task 1, it's 115 stuff, but with testing, and testing is kind of the new thing. Java's the new thing. Just getting used to the course, getting warmed up to the course. Task 2 is the first 116 content. You're working with classes and object-oriented programming, but it's creating 3 classes, writing tests for classes. It's not much. And then Task 3, it's the first time you're actually asked to do something moderately challenging. So I say moderately. It's fairly challenging, though. Removing a node from a linked list is the challenging part of it. But anyway, that's where we're at in the course. Let's get into some more content. We're talking about trees this week. New week, new content. Oh, Wi-Fi, work with me. Where's my thing? It's in my pocket. Okay, so any questions before we get into it? Could it be because of daylight savings? It might be. Daylight savings is a nightmare for testing. I know not to make the mistake these days, but for lecture questions, my lecture questions were off by an hour before because I didn't account for daylight savings. So I'll upload all the lecture questions to AutoLab at the beginning of the semester, and anything after daylight savings was off by an hour. So I know these semesters, I can handle that, but daylight savings and time zones have claimed many budding programmers. Those are really frustrating things to have to deal with. Leap years, leap seconds, so many complications when it comes to timestamps. Okay. Do they have signal jammers in this room? Yeah, it's all of us. I think it's just I don't want to rant about it. I feel like I ranted about this too much. I haven't ranted this semester yet, but it's like the network is shocked every time we have a room of over 100 of us all using the Wi-Fi. The internet's the Wi-Fi is I didn't know I was going to have to do this much work. I'm not doing it. Every single time. I don't know. I'll leave it at that. But it's no surprise that we're all going to, like the first day of classes has actually been pretty good the past few semesters, but the first day of class, it seems like the Wi-Fi always goes out. Like nobody's expecting a whole bunch of students to show up and start using the Wi-Fi. But anyway, it seems to be decent right now. I mean, at least I'm connected. My music didn't come on to turn off to end the previous lecture because I had no Wi-Fi at all. Okay, so let's talk about binary trees instead. That's what we're actually here for. So binary trees are very similar to linked lists. We talked about linked lists. They work off references. They're nodes that have a value and a reference to another node. Trees are very, very similar to that, except having a reference to one next node. It has references to two nodes. And that's it. That's the difference. Other than that, they're basically linked lists. So we have a reference to two different nodes, and we call these right node, left node, or child nodes. And in relation to the child nodes, we call the node referring to it as its parent node. So a little bit of terminology. And with trees, there's two parallel analogies that go through all of the naming for this. One is the family tree one that's on screen, parent nodes, child nodes. This extends to grandparent node, descendant, nieces, nephew, like the whole family tree analogy all extends to this. And for our purposes, I'm going to use child and parent. Actually, I'm probably just going to use child. I don't care about parent nodes too much in relation to what we're going to talk about. But child nodes, I'll say that a lot. The other ones, the extensions, I'm not going to, but if you get into more tree research, like in 250, 331, they might use more of the expansion of this analogy. The other analogy is trees in nature, root, branch, leaf. You're going to hear those terms as well. The biggest one that I'll use is root, meaning the first node in the tree. Just like head of a linked list is the reference that we store in our variables to store a linked list. The root is the first node of the tree. So vocab out of the way. Let's talk about these things. Here's an example of one such tree. Again, just like a linked list, except instead of value and next, we have value and left and right. References to two other nodes, up to two other nodes. We're specifically talking about binary trees here. The bi meaning two. We can't have trees with more than two child nodes. Those just wouldn't be called binary trees. So we're talking about binary trees only throughout this week. So this is a binary tree. Just like linked lists, these left and right are instance variables that store references to other binary tree nodes. And they can be null if there is no left or right child. And this is also a valid tree. I used to only show the other one. The other one is the one I'll use throughout my lecture examples. But this is a valid tree. When I only showed the other one, students always assume that either left and right are both there or they're both not there. That is not the case. I can have a left node but no right node, a left child and no right child, or a right child with no left child, or neither, or both. All four situations are on the table. So without explaining this, I would see in the code so often, if the left is not null, then go to the left and to the right, but then right was null, and you get a null pointer exception. So make sure you're checking each of these child nodes before you try to do anything with that reference. So this is a valid tree, but this is the one that I'll use for lecture because I think it looks prettier on a slide. No other reason, but it's a nice, symmetric, balanced tree that we have here. For the terminology, I won't use much of this terminology, but just to put it out there since I mentioned it, root is, like this would be a variable in my code somewhere that stores a tree. Root is a reference to the first node in the tree that starts the whole thing. A branch would be a path from the root to one of these nodes that have null, left and right both of null, which we call a leaf node. So the natural tree analogy is there as well. I think it's, I don't know, it's fine, I guess, that there's two separate analogies, but it's double the amount of vocab we have to remember. Which is fine. They're both pretty natural, so I don't think it's too big of an issue in this case. And here it is in the code. There it all is. Binary tree node, just like our linked list node, it's going to take a type parameter. We're going to have a value of the type matching the type parameter. a reference left to another binary tree node of the same type, and a reference right as instance variables with a reference to another binary tree node of the same type. Constructor to initialize all three, and that's it. Unlike the, I was missing the P there. All right. Unlike the linked list node class, where linked list node, we added a whole bunch of algorithms into that linked list node class. This is our binary tree class. We're pretty much done. The only thing we're going to add is getters and setters. That's it. But this is all we need. Our binary tree node isn't going to have any functionality itself. Granted, we could have done the same thing with the linked list node. We just decided to put some code inside there. But for binary trees, we're going to have all of the algorithms outside of the binary tree node class itself, except for this main method. I do put this inside the same class. And then to create a binary tree itself out of these nodes, we're going to make them manually. For binary trees, we don't have any clear insert method. With linked list, we had prepend and append. We had two ways to insert into a linked list. We're not going to have such a clean answer for trees. If I have a binary tree node, I can create the first one, and then if I say root.add and then some value, where do I add that value? Do I go left or right? And how do I, if there is a right and left node, like how do I traverse the tree to figure out where to insert this new value? There's no clear answer to that question. On Wednesday, we'll talk about binary search trees, which will have an answer for it for specifically binary search trees. But for a plain old binary tree, we don't have any clear answer as to where we should insert things, so it's hard to write an insert method at all. We're just going to create our trees manually. So I'm going to create the tree. Since this code is in the same class, this is in a main method in the binary tree node class, even though on the slide it's not super clear that that's the case. In the repo, this example is inside there, which means I can access left and right directly. Root.left equals, so I'm setting left equal to a new node to set that left child, or to set the right child and the left child, and then root.left.left, set that equal to a new node, and build that tree that we saw on the previous slides. Root.right.left, set that left child of the right child of the root to a binary tree node containing the value 7. So I'm building the tree manually as I go through this. If this code was not in the same class, I would just have to use my setter methods. I would just say root.setLeft and then pass this new node as a parameter. Root.getRight.setRight, etc. And that's our tree. That's kind of it. Is circular binary tree exist? It could, but we don't want it to. It would be it's usually a bug in your code if you end up with a circular linked list. I feel like y'all asked this because it was an interview question for linked lists. You're just trying to get interview question answers, but I'm still going to answer this. Is if like right down here referred to the root, then I would have a circular tree. I have a loop in my tree, and it makes it, technically it's not even a tree at that point. It would be a graph, something we'll talk about later in the semester. But if you work, like the code is going to allow you to do that. You could physically do that, but when you run your algorithms, it's going to get stuck in this loop and go infinite, and you're going to time out in Autolab if you submit like that, because your algorithm's never going to end. Okay. Anyone have any questions? Because this is all I have to say about the structure of a binary tree. And I don't think there's anything too new. We have 2 references instead of 1. Other than that, it's everything you know about linked lists transfers over. So this is all I have to say about the structure, and then we'll talk about algorithms. What are the implications of the structure, and how do we work with these trees? That's what I want to spend the rest of the week talking about. But any questions on the structure itself before we get into that? Yeah.
Because I know in this example you made the binary tree in the binary tree node class.
Mm-hmm.
Can you make a binary tree out of the class?
Yes. Yeah, you just have to use your getters and setters. So since I'm in the class, that's why I'm allowed to say .left, .right. So we usually don't access our instance variables directly like this. But I'm getting away with it. Probably should just update the slide to use getters and setters, to be honest. But that's why I get away with it here, because the code is in that class. Even though the slide doesn't show it clearly, because I closed the class, it looks like this is outside of it. I don't know. I think I just got to update this slide now that I think about it. Because why do I do something silly and then explain myself in the bullet points? Yeah.
Would there be a way to check if something is a binary tree or a linked list based on
Is there a way to check if something's a linked list or a binary tree node? Yes. In general, it'll be like you'll write a method that takes one or the other, and then the compiler is going to check for you. If you try to give it a tree, if it takes a linked list, you're going to get a type mismatch error. So it just wouldn't work. If we had a generic like node class and binary tree and linked list both extend that, there are ways that you can check the specific type of an object. But I don't want to get into it. You can get the... Actually, I'll get into it a little bit because I can give a quick answer with this one. Kind of like the toString, the default toString will give you the class name. It'll give you the actual class name even if you're coded to a base type. I haven't introduced any of this stuff. There's a way to check the types. I'll leave it at that. Yeah, I'd have to explain way too much. Ask me again in Polymorphism Week. We can talk about it a little bit more. Okay, so that's the structure of a tree. No questions on that, so let's move forward. What are the implications of this? And my big question is, how do we work with this data structure? So we have data, we put it in a tree, go us, that's fine. But how do we work with this data once it's in a tree? How do we navigate this thing? Specifically, we can't use our linked list methods. Our linked list algorithms always just did something at a node, went to the next node, did something there, went to the next node, did something there. Once next was null, it started returning back up the recursion and gave the final answer. But with a tree, how do we decide if we're going left or right? We can't just go to the next node because we have two next nodes to go to. How do we handle that? And the answer, it's going to be recursion. And we're going to make a recursive call to both child nodes. Easy day, done. We're going to make a recursive call to both child nodes. So let's apply this to the simplest algorithm that we can have of just visiting every single node in a tree. So we want an algorithm that's going to visit every node in a tree. We're going to build specifically toString and convert the whole tree to a string. But it's a proof of concept that shows that we can write an algorithm that visits every single node exactly one time, keeps track of where we are in the traversal of the tree, and traverses the nodes in a specific order. And we're going to see three different orders for that: pre-order, in-order, and post-order. So let's talk about this. So here it is for an in-order traversal. I'll go through all three of these. In order, and they're all very similar. In-order traversal, what we're going to do here is make a recursive call. We're making two recursive calls, one for left and one for right. We're going to make a recursive call on the left node to handle everything for the left node, handle the node that we're currently visiting, and then make a recursive call on the right child. And here we're effectively doing toString. So if we're saying in-order traversal is going to return a string, make the recursive call on the left node. That's going to return the left subtree. Oh, I didn't introduce that terminology. The left subtree as a string. I always forget to flip my directions. The left subtree as a string. I'm going to concatenate that string to what I'm returning, convert the node's value that I'm currently visiting to a string, concatenate that, and then go to the right subtree, convert that whole thing to a string using recursion, and then concatenate that to the output as well, and then return the output. And I'm not checking if right or left are null here. So we have to be sure that we're always checking if our nodes are null. And we can do that in two different places. I can say if left is not null, then make a recursive call. If right is not null, make a recursive call. I'm doing it a little bit different. I'm not checking if left or right are null. I'm just making the recursive call on them. And then the recursive call, the first thing it'll do is check if the node is null. So I am still making my check. It's just a matter of where I'm making the check. You can make that check wherever you want, as long as you do make the check. Just like linked lists, everybody getting all the null pointer exceptions in Autolab for days. Same thing with trees. You're gonna, if you're not careful, you're gonna see some null pointer exceptions. Be very careful. Never just assume that a reference is not null. Always assert that it's not null if it's in your test cases. Assert that it's not null. If you assert it's not null, or in your code itself, if, check with a conditional instead of an assert, if it's not null. Here, if node is not null. Now, in this code block, I'm guaranteed that node is not null because I would never get into this code block if node was null. So inside this code block, I can safely say node dot. I'm not going to get a null pointer exception when I hit this dot operator because node's not null. So before you call the dot operator on any of these node-based data structures, on any node in these node-based data structures, before you use that dot operator on them, make sure the thing isn't null. Always, always. Check this. Check, check, check. So many null pointer, every semester. I say a lot in lecture, but every semester still, there's so many null pointer exceptions, starting with homework 3 when we do linked lists. So many. Okay. So hopefully I say it. Maybe I just got to say it twice as many times in lecture. But make sure you're checking for null. I know this dot operator isn't going to cause a null pointer exception, but left here might have been null. So this might have resolved to null. So when I make the recursive call, check if it's null. If it's null, don't access anything of that because it's null. I don't want a null pointer exception. Just return empty string. And then to start everything off, call in order traversal. Oh, man, I lied earlier in the lecture. I forgot, we put our traversals inside the node class itself, the binary tree node. So the binary tree node will have these 3 algorithms. I forgot that we did that. I don't like them in there, but it is what we did. Okay. Pre-order traversal. Same, almost exactly the same thing, except the difference is when we visit the node, when we get to a node, when do we actually process the value of that node? Pre-order traversal is going to process the node, then make the 2 recursive calls. Post-order traversal is going to make the 2 recursive calls and then process the node. And the first one, our in-order traversal, was make the left recursive call, then process the node, then make the right recursive call. So there's 3 places where this handling this node can go: before, after, or in between the 2 recursive calls. And no matter, depending on where we place it, we call it a different traversal: pre-order, post-order, in-order. So conceptually, we're really only learning one thing, just one traversal, but there are 3 varieties of these traversals. And when we do a traversal like this, it is guaranteed that we are visiting every node exactly once. I guess I can't say guaranteed because the silly things like the circular trees, disconnected trees, I guess you could have. But we're going to visit every node, and aside from weird situations, we're going to visit every node exactly once. I sure do love null pointer exceptions. What do I want to say? Yeah, null pointer exceptions are frustrating. Wait until you get to, not to scare you too much, but when you get into 220 and you start seeing segmentation faults, the old seg fault, you will hate those more than null pointer exceptions. To this day, I don't like coding in C because I have nightmares of seg faults. Since I brought it up, I should give a brief explanation. Seg fault is, C will let you do pretty much whatever you want, and if you do something really dumb, it'll yell at you and slap your hand and say, we can't do that. A seg fault means you're trying to access a memory address that you weren't allocated. So it's not on your stack, it's not on your heap, but you say, give me the value at this memory address. It's going to say seg fault, which will happen a lot. You will see seg fault. If you make it through all of 220 without seeing a seg fault, you deserve an award. let me know. If you get to the end of 220, come back to me. If you've never seen a single seg fault, I want to know about it. So with in order, would it check everything down the left and then go to the right through the bottom and do the same thing? Yeah, so it's going through. So this is the power of recursion. We're going to start really seeing the strength of recursion. With an in order, we're going to go to the left. Just one recursive call, it looks like we're visiting the left node. But what it's going to do is visit the entire left subtree. So we're going to go to the left, but since it's a recursive call, left is going to go to its left, visit its node, and visit its right. And both of those calls are also recursive. So it'll recursively go down all of the child nodes, all of the descendants of the left node. And then once that finally returns, we might have handled 1 million nodes in this one call. Then we'll finally visit this node, and then we'll go to the right and do the same thing and handle possibly 1 million nodes over to the right. That's the power of recursion. It's going to do a lot of work for us. Yeah. Possible. I'll say anything's possible. If you write enough code, you can do whatever you want. With a nice clean, like 5 lines of code, well, it's more than 5 lines of code we have it written here, but with this code, it will go left, 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 left. If we want to add some extra logic in there, we could do something else. But as written, it's going to go left, 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 until left is finally null. Then it'll start coming back up and going to the right. Okay, so here's the code. Here's all 3 traversals, all very similar code. What value do you get from having each of the traversal methods? Depends on your exact application. We haven't talked about why we would use a binary search tree yet. We'll get into that Wednesday or binary trees yet. We'll get into it Wednesday when we talk about binary search trees. We'll give an example of when we would use these things. But it depends on your specific application which traversal you would use, because you might want to visit the nodes in a different order. The most useful one for us is going to be in-order traversal. Pre-order and post-order have their uses, but they're a little more niche. In-order traversal is going to give us really what we want for our purposes. So here's all the code, very similar for all 3 of them. As I just said, in-order traversal will be the biggest one. I'll foreshadow it a bit with binary search trees. In-order traversal is going to visit all of the nodes in sorted order based on a comparator. We're going to tie in that comparator, inheritance, and binary trees. We're going to tie all that together on Wednesday in in-order traversal to visit nodes in sorted order. So here's all the code. And for each of these, it's pretty clean. We use a few more than 5 lines of code here, but usually this would be 5 lines of code. If node... We'll see it for the memory diagram, actually. If node not equals null, skip this one, make the recursive call, and then just print this directly to the screen instead of collecting all these in a string. Then recursive call, and then close brace, and that's it. And we don't have to return anything in the else. So we can get these down to 5 lines of code if our goal is to print everything to the screen in this tree. 5 lines of code. Try doing this without recursion. You recursion non-believers who will say, I'll never use recursion. I'm using a loop for everything, and who use the loop for all of task 3, all of the linked list stuff. You're like, well, node not equal null. That's good enough for me. Try writing one of these without recursion. I've had students, it took years before anybody took me up on this challenge, but I've had, I think, 3 or 4 students in the past now who've taken me up on this over the past few years. And their solutions are always 20, 30, sometimes 50 lines of code to be able to do the same exact thing that we do here. The recursion is saving us a ton of work. If you're doing recursion, you have to keep track of where you are in the tree, which nodes you visited, how many times you visited the node. So notice that we're getting back to this node 3 times. We're visiting it the first time we get to this node. We're making a recursive call. The second time, we're handling this node, and then we're making a recursive call. And then the third time, we're just returning. We're getting out of there. We're already done. So each node you're visiting 3 times, so keeping track of where you're at in all of that process. With recursion, the stack frame's keeping track of that for us. And it's doing a lot of bookkeeping for us. If you want to write these without recursion, you have to do that bookkeeping, and it's way more of a pain to the point where you're going to use recursion. And this is where it's, if you haven't gotten used to recursion with linked lists, when the recursion was, it was easier, but it's not like the recursion is too much harder here, admittedly. But you do have two recursive calls, which can get trippy. I don't know. But if you couldn't handle the recursion for linked lists, you're in for a treat when you start doing these recursions. I don't know. I couldn't imagine doing the tree traversals without my very first recursive methods. But nobody listens to me during linked lists, so these will be your first recursive methods for most of you. I shouldn't say most, but most of you who come to office hours asking questions and are struggling with task 3. I rarely see someone struggling with task 3 who is trying to use recursion still. And that's not entirely fair, because I know a lot of you try using recursion and then say, I'll do this later. I just got to get through task 3. Let me use a loop. That's fine. That is what it is. But you're going to want recursion now. Now is that time where you want to use it. All right, so let's talk about these things a little bit more. In order traversal, let's talk about the order in which we'll visit these things. In order traversal on this tree is going to make the recursive call to the left. So the very first thing on the root's not null, make the recursive call to the left. That's going to make the recursive call to the left, which makes the recursive call to the left. So we go left, left, left. And then left is null. So this is false. And we return empty string. Return empty string, concatenate -3 to the output string. So -3 is going to be the first node visited. And then recursive call to the right. That's null, so it does nothing. And then this returns back to this stack frame. It just got its left return, so we could visit 2. 2 is the next output. Right recursive call, left recursive call is null, does nothing. Visit 4. Recursive call with null. I'm using boxes to represent null, by the way. I hope that was clear. Null, returns. This is done, returns. This just got its return from its right recursive call, so it's done. Return, visit the root node. After visiting the whole left subtree, we finally visit the root node, and then make the right recursive call, left recursive call, left recursive call, return. Visit 7. Right recursive call does nothing, returns, visit 8. Right recursive call, left recursive call, visit 14. Right recursive call, return, 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 and finally return this full string back to whoever called this method. Oh, someone gets music. I don't get music, but someone's got to work it. For a pre-order, we're going to visit the node, so we visit the root node first. Left recursive call, visit 2. Left recursive call, -3. Left recursive call, nothing, return. Right recursive call, return, return. Right recursive call, visit 4. Nothing, nothing, return, return. Visit 8. Left recursive call, visit 7. Return, return, return. Right recursive call, visit 14. Do nothing, return, return, return. So we get a little bit different order. We're visiting the node before making the recursive calls. Gives us a very different order. And then, I can't even click. And then post-order, we do the recursive calls first. Recursive call, 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 return, return. -3 is first. Return, right recursive call, left, right. 4 is next. Return 2, return, recursive call, left recursive call, left recursive call, right recursive call, visit 7. Return, right recursive call, left, right, 14. Return 8, return, and 5. The root is going to be last in a post-order traversal. Okay. Okay, so that's my very quick diagram, just pointing with the mouse. Let's see it in a memory diagram. We'll do this one a little bit slower so we can see exactly what's going on. Those 3, I just want to show the different orders, that we will get 3 different orderings of all of the nodes, and just give a brief taste of how these traversals work. Let's do it again with a memory diagram, and I'm going to visualize the tree here, and do the whole memory diagram thing over here. Again, no tracing tool because there's no way I can finish a diagram. I still don't know how Paul does it. I might have to watch him do one of them to see where he's saving all his time. Maybe he just types faster than I do and doesn't get sidetracked. But okay. So constructor, we've seen plenty of constructor calls, so I'm only going to go through one of these. But new BT node for binary tree node, I'm doing that just for this slide because this line right here would be way over here. It would just be massive. This line would be way over here. Just doesn't fit on the slide, so I'm abbreviating it for the slide. So new binary tree node, constructor call. This is a reference to the object being created. We have 3 instance variables, which I removed from the slide again for space, but value left, right, value left, right. The constructor initializes, I removed the whole constructor. The constructor initializes all 3 values. So we have day, null, null. I'm going to do root.left. So root.left, this constructor is going to return to a variable that's on the heap, which I don't think is, I don't recall off the top of my head, something we can do in the tracing tool. So this return arrow, I'm never really going to sweat return arrows on the memory diagrams for the quizzes. If you lose credit because you missed a return arrow or all of them, and everything else was right, please come to me. I'll change that grade. But this return arrow would go to a variable on the heap. And root.left. So root.left equals whatever is returned by the right-hand side. So we have a constructor call and all that stuff, and then it's going to return to left. And instead of being null, left is now OX200, a reference to this new node that was created. Same with right. Root.right equals. So we set that equal to a reference to the new node that was created. And then root.right.left, root.right dot left equals a reference to the new node that was just created. So that's how we're building this tree. That's what this dot right, dot left. Now, if I wasn't in the binary tree node class, this would be set left, set right, root dot get right dot set left to this. So we'd have to do a little bit different using our getters and setters. But with dot left, dot right, this is how we would do it. All right, so we have our tree, and let's call our traversal. And this is the 5-line version of the traversal. Not much code going on. Again, write this without recursion. It's going to be a lot more than 5 lines. Maybe that should be the new challenge. Try to write it without recursion in 5 lines. You guys are destructive. What are y'all even doing here? All right. No, I actually did get distracted by that. I was trying not to. All right, so we're going to call it traversal. If you can do that, that should be my new challenge. If you can write this in 5 lines or less without recursion, I'd like to see that one. That one would be a very, very difficult challenge. All right, but let's start our traversal. So we get a traversal stack frame. The way we're doing this, we're calling traversal with a reference to the node we're visiting, which will be root OX350. And if node not equal to null, node is not null. So we're going to go into this stack frame. Yeah, that's what I'm saying. I don't remember off the top of my head if it's even possible to have a return arrow to the heap. I don't think it is. I'm just not 100% on that. On a quiz, we shouldn't do that anyway because we should be using getters and setters. So it shouldn't even come up on a quiz, but I don't know if it's possible. And if you miss a return arrow, I'm not going to sweat it anyway. So we're not going to worry about it. Okay, so if node is not null, node is not null. It's OX350, definitely not null. So we're going to get into this. And traversal node dot left. So node dot left. And traversal is static. I forgot to mention this. Traversal is static here. The only reason I have traversal static is because I didn't want to write this in every single stack frame. So not the best reason. But for what it's worth, it should be static, so I guess I'm not mad at myself for that one. But traversal of node.left, so we have a recursive call on node.left, which is 200. That is not null, so traversal of node.left in this stack frame, it's always the top of the stack that is the active stack frame. So this stack frame, node, when we're resolving node, it's always in the active stack frame, is OX200 dot left. So null is going to be the input of the next traversal. Traversal node equals null is going to be the input there. And at this point, we have 3 recursive stack frames on the stack, and all 3 of these stack frames are remembering where they're at when they get control back. And this is where the recursion in the stack frame is doing the bookkeeping for us. Now node is null for this active stack frame. If node is not equal to null, that's false. So we skip this. We get right to the bottom of the method. Method returns, stack frame is returned, and this is crossed out. When I gray out my stack frames, that's the same as crossing out. I just want on the slide for you to be able to read the old values of old stack frames. So we return, and when this stack frame gets control again, it remembers where it was. This was always the case, but it's going to be more important now because we have 2 method calls in the same method, 2 recursive method calls even. So when this stack frame gets control again, it's going to remember that it was right here, that it just got the return value from this recursive call, which didn't return anything, but it resolved to void, which is all we need here. And then it moves on to the next line. It makes the right recursive call. So it makes the right recursive call. OX200.right is null. Makes the right recursive call. That's null, so it does nothing. Returns. Gets back to this stack frame for the 3rd time. This is the 3rd time we're in this stack frame. This is the bookkeeping you would have to do if you're not using recursion. 3rd time we're visiting this, but the program pointer, which remembers which line it's on, knows that this recursive call just returned. This one just ended, so it's going to continue where it left off and print this node's value to the screen. Prints that to the screen. Gets to the end of the conditional, end of the method. That's the end of that stack frame. It returns and gives control back to this node, which was patiently waiting at traversal of node.left. That just resolved, so it knows to go on to the next line, traversal of node.right. So node.right, OX480. So we have a new stack frame where node is 480. It's not null, so it's going to make its left recursive call, 480.left. It's going to make a recursive call with 936 and remember where it is in its execution. This 936 is not null, so it's going to make its recursive call to the left. So this node, we're in this stack frame going node.left. Is null, so we make a stack frame where node is null. That's going to do nothing and just return. Get back to this stack frame. It just finished with this call, so it's going to make its right recursive call. Node.right is null. Put a stack frame on the stack for null, and right here is where I want to chill for a second. Now let's take a look at this. So, and this is the most complicated that this memory diagram is going to get. We have 1, 2, 3, 4 recursive calls on the stack, plus the main stack frame still. And these stack frames are all mostly at different parts of their execution, and each one is remembering where they're at in their execution. So this stack frame, the first one that was called on the root node, on this node, it's sitting right here at this line waiting for its node.right recursive call to resolve. So once this stack frame gets control again, it's going to go on to print out what its value is. This stack frame with 480, I color-coded these. There it is right here, the medium gray arrow. But it's sitting right here at the left recursive call waiting for this to return. So it created this stack frame, and it's waiting for this stack frame to resolve so it can continue on with its right recursive call, and then when that returns, it'll print out its value. On this stack frame, this is sitting right here at the right recursive call. It made its recursive call to its right child, which is null, and it's waiting for this recursive call to resolve. And when it does, it's going to pick up its execution right here and print out its value to the screen. And then we have this recursive call where the input is null, and it's about to do nothing and return and remove this stack frame. So a lot going on at this snapshot of the memory diagram. Are there any questions on how all of that is happening? Is everyone falling in love with recursion yet? It's a lot going on in this. Yes? Probably. The question, would you instantly fail if you mess up one or two of these recursive stack frames? It depends exactly how it goes down. But yeah, pretty likely. Like the tree, I'll give a little bit of spoilers. The tree quiz should be pretty much this. Like, can you handle going through a traversal of a tree? So there's not a ton that we're asking. And if you mess up the recursive calls, like that's most of what we're asking you to do. That's probably going to be a fail. And if you do the traversal in the wrong order, this is surprisingly common. I don't know how so many students mess this up. Don't mess this up, please. But take a look at the code you're given when you get to the quiz. Is it an in-order, a pre-order, or a post-order traversal? Like, make sure you do the right traversal. If you do the wrong traversal, like that's an easy fail. Like, you didn't even look at the code. And I see that too often when students just copy what was in the lecture notes and do that, and then it's a different traversal, and it's an obvious fail because they clearly didn't trace the code at all. And then, so this returns, prints, returns, prints, returns, just cleans everything up, and we get to the end of the memory diagram. Oh. Where are we? There we are.